To reduce the minimum output voltage to ensure everything is in saturation region, we can apply that. We can separate the gate bias voltage for the cascode device shown in here. So VB is generated from somewhere to properly generate to maximize the output signal range. So here the diode connection is from here to bottom transistor shown in here. In that case, this is because of this is still cascode structure. The R out would be RDS2 times GM4 RDS4. What about the minimum voltage V out mean? So V out mean would be here one VDS2 and another VDS4, right? Let's say find the critical limit for the operating point. So that would be VTH plus V overdrive, and the minimum case is V overdrive here, and we have for the same size of the device we will have a VTH plus V overdrive here. That one between VDS we will have also overdrive voltage there. So if we design VB slightly greater than how much? 1 VGS here, so 1 VDS here, 1 VGS, so V overdrive plus VTH plus V overdrive, right? If you set it VB slightly greater than that, the V out mean would be what? 2 overdrive. So there is no factor of the VTH term, so we can have a very smaller minimum output range, minimum output voltage out of this cascode device. So this kind of cascode biasing scheme is called the high swing cascode. High swing mean by reducing minimum requirement voltage here, we can have a larger voltage headroom. The signal can swing much larger range. Okay, by having higher output impedance looking down onto the drain, we have a very high output 1 over R out, right? So previously we will have like 1 over RO, but by having cascoding we can have a much flatter current source. This would be more ideal current source. Okay. For high swing cascode, how we generate the VB. So as I explained, for now, for assuming for n equal to 1, we have the same size of the cascode device and bottom transistor. In that case, how we generate the VB. So if you look at the VB, in that case, the VB must be greater than how much? 1 V overdrive plus VTH plus V overdrive. So meaning VTH plus 2 overdrive voltage. For the same current shown in here, same current flow, I0 and I0, we want that VB 2x larger overdrive compared to other devices, right? All these devices, 1 overdrive voltage will be set up between gate and source. So that should be how much? VGS must be greater than VGS is equal to VB, right? So VB that must be greater than VTH plus 2 overdrive voltage. So the size must be how much how small it should be. That should be the W over L must be 4x smaller, right? Because as you can see, the I0 is 1/2 mu n COX W over L overdrive voltage here, If you want to have a 2x larger overdrive voltage, that results in 4x larger. For the same amount of current, if you want to make it 2x larger overdrive, meaning W over L must be 4x smaller, right? To make it the equal current. All right. This is something that how we size the M5 device to generate the proper VB. In some case, n is greater than 1, so that the cascode device size is smaller than bottom. Device size is smaller than bottom device than that of why we are doing this? Because we want to reduce the drain parasitic, so reduce a drain parasitic at the output, right? In that way, we have a smaller device. If this becomes smaller, then we will require even smaller M5 to have the larger, higher VB voltage. Okay. For n equal to 1, so we need M5 to be 1/4 of the W over L. So actually smaller than this number. So how we actually implement this kind of a small size for this M5 for better device matching? So if you just let's say draw the transistor here and then 4x large, 4x smaller, you will have a smaller device, right? You can draw that 4x lower device, but the problem is device characteristic in actual submicron device process. The device characteristic vary. Characteristic varies for different dimension. Meaning VTH are different VTH. Even in the same process, for the different size, different VTH you may see. So another way to scale down this kind of things is that you, instead of making smaller L, you make a 4x larger L. So for 1/4, for example, L, you can make it W over 4 times L. So one way is to from here to like this. Again, different dimension results in different VTH. So this is also not good because the different characteristic. So a good another better way is to use the same device. So use for example like this device, use the same device in series, right? Like this. Then it is drain and source, so drain, source, drain, source, drain, right? drain, source and drain, right? Like this. You can have a series connected transistor. So single transistor to W over L to series connected devices, W over L, W over L, W over L, W over L, but share the input gate voltage like this. For example, you can add that as much you want for a better margin. So your drawing device with the identical device structure like this, 1, 2, 3, 4, right? Like this. So this is the drain and source, and this is drain and the source, the drain and source, right? So source and drain are connected each other. It's MOS like this. So if you place as many devices as you want, you can have easier control. Have a better matching the device. You are better match the devices between what? This device and that device and this device, and all these devices matches better, and sharing same. So sharing same dimension meaning same VTH characteristic. Take for a corner variation, okay. Like a or PVT, process voltage and temperature variation, we will see same VTH variation, right? Okay, this is the typical way to implement this kind of amplifier, this kind of a current source. If you want, so we have a cascode device to boost the out. If you want an even higher output impedance, you may introduce amplifier here, gain of AV. Then the output impedance is boosted by gain. So this is gain that the RDS times RO times GM RO. So we have a GM RO here, and we have AV here, so we have additional gain. So this kind of a amplifier, for example, how we get this. So let's say we apply the test voltage and current here, IT here, RO, the voltage here will be IT times RO. Such voltage is amplified by that, so that node would be IT times RO times AV. And now we know that this is IT, so voltage difference between gate and source must be IT over GM, right? IT over GM. So voltage relationship IT over GM is same as AV times IT times RO minus IT times RO, right? So from that equation, we have addition RO here. And then the voltage across the, I'm sorry, this is the not IT. The current through this would be, let's say, ID. So this is the, through the RO, that will be IT minus ID. So that will be ID over GM. So ID over GM. And this is the first equation. And the second equation for the VT. So VT equal to what? IT minus ID times RO plus IT times RO, right? From 1 and 2, you can drive that. So here we have the additional variable here, right where. So IT, we have a relationship between IT and ID, right? So equation 1. So we wanna eliminate the ID. So ID here from here, ID equal to GM times IT AV RO minus RO. So minus 1 RO, right? So plug that into the second equation. So here, that means the IT minus 1 minus GM AV minus 1, right? RO square plus IT times RO, right? So we have factor here, here, and here, and here. So the VT over IT, that would be R out, would be RO square. This dominant term shown in here, RO square. Let me write down complete equation. RO here from RO and RO square 1 minus 1 plus, let's say GM 1 minus AV, right? So that would be RO squared times GM times 1 minus AV. So as long as AV is high and negative, then would be that close to that one, right? So that would be absolute. So AV is negative gain, high negative gain. Then our gain, the output impedance, would be approached to that one. So this is just something that you can have. AV is negative, so you can boost the output impedance even higher out of this cascade biasing. Okay. So the gain boosting amplifier we designed here, common source amplifier, just take the source node and amplify by GMRO here, and that goes into the gate, right? The cascade device. So this is boosting amplifier. So the final output impedance would be what? GMRO. So RO is boosted by GMRO, right? And then another boost from the M6. This is from M4 and this is from M6, right? So that would be even higher output impedance out of the gain boosting. For the current mirror, if you want to construct current mirror, we are using the similar boosting here, but the difference is the gate is tied to gate voltage tied to drain of the M3, so that we construct the diode connection so that we have a mirroring happen here. Other than that, left and right is balanced. Okay. You can double check the polarity of the amplifier by using perturbation analysis. By the following: you increase the voltage than greater than Vref will result in higher voltage on the output of the amplifier. That will reduce the second, that will increase the gate voltage there, so that the drain voltage, that will increase the current. That means that we bring down the voltage on the drain again, the third. So up and down balanced by the feedback, right, until this voltage variation approaches to zero, right? The gain is ideally infinity, so 0 volt times infinity will provide us a constant value, constant voltage on that node, right? So negative feedback finds proper bias, gate bias, to ensure that the loop is stable, right? So far we just learned about how we properly generate the current source and bias, but in reality the actual current source, many places we want that to be properly biased. In actual device design, the required current source and biasing can be far away, separated. So one way you can think of is voltage biasing, meaning you generate the VGS here, you route this long wire to bias this current source. This is the one way. This is the problem with this kind of a thing, is that if you have this kind of a long wire design, then you will have a definitely supply resistance. So on the supply network, so non-zero resistance, all the current flow, let's say I1 and I2 and I3, all these current will flow through the resistance 1, 1, 2, I3. That will bring up the voltage drop. So even though you have a VGS generated here, this node voltage will be same as Vx, because the current is 0, right? Because the gate is all capacitive. So this is just capacitive. The same voltage Vx will be delivered to all the other devices. But the problem is the gate source node voltage will be different, right? For different cases. Since if there is non-zero resistance on the ground network, there you will see different VGS 1 and VGS 2 and VGS 3. So you cannot guarantee I0, so I1, I2 and I3, I0, right, for a large R. So another way to properly deliver this kind of a biasing is that we deliver the current instead of voltage, shown that. So we closely lay out where it is needed, so the R is 0, so that we deliver current. So long wire here, even though there is a resistance there, so even though resistance there, voltage drop can be small and well controlled, enough to ensure that the PMOS in saturation. In that case, even though there is large resistance there, right, this is a current I0 flow, voltage drop is there, I0 times R in there, still VGS is properly set up there, then we can guarantee that I0, all the I0 are the same, right? I1, 2, 3. So I1, 2, 3 are all the same, right? Like this. In the previous voltage bias case, since all the current is lumped and flow back to the original source, this kind of voltage drop across R will impact on the source node voltage. But for the similarly for the gate resistance on the line here would not be a problem because there's no actual DC current flow. So this, even though large resistance there is always 0 voltage drop on the voltage here, right? This is a different way of biasing. So we prefer current biasing for this way because we have to distribute, typically we distribute the biasing to many places, right? Long distance bias. Okay. Meaning insensitive to supply resistance, the wire resistance. Okay.